All right, let's do an example. So a researcher believes that a plane which is lost has gone down somewhere in the desert, and that the joint PDF that describes the location of where this plane has gone down is this guy. Okay, it's the joint probability density function. Okay, the x and y here are they describe the x and y coordinates. You can think of them as longitude and latitude on a small scale or something like that. Okay, maybe this is due to this researcher's expertise and knowledge of the area and the layout of the land and the mountains and all this stuff. Maybe they believe that it sort of has this kind of a form, so that it's some constant k times x times y times the indicator that both x and y are in the unit interval. Okay, so maybe the units on this these numbers are, maybe they're 100 miles. Okay, something like that. So 0 miles up to 100 miles in each direction, something like that. And this is for all x and y in the reals. So what we want to know is, what's the chance that the plane is found in region A? Maybe we want to know that because maybe we can search region A pretty easily, and we want to know, hey, what's the chance that it's actually there? Okay, so first thing we need to do is find the value of the constant k. K is it's a constant. It's a scalar. It's a scalar. It scales this density function. We need to scale this density function in the proper way so that it satisfies the axioms for probability density functions. It's got to integrate to 1, right? So what I'll do is I'll just set 1 equal to the double integral of that density function over all reals in all directions. Okay. Now I'm going to substitute in my expression for the density function there. It's just k times xy times that indicator function. But now this indicator function really tells me how to write the limits there, right? By the way, I can pull the k out. I can pull the k all the way out because it's constant with respect to both x and y. So I can write like this, I think. Right? And remember what this means. It means to do this integral first. I'm going to use some red parentheses there. They're not absolutely necessary, but helps us to see what's going on. Okay? So how do you evaluate this integral? Well, this will be k times, let's see, you know what? This y is constant with respect to x. It's a variable, but it's constant with respect to x, so I can pull it outside that first integral. See that? Now I can just do that integral on the inside. Okay, it's just going to be x squared over 2, 0 to 1, dy. All of this is just a half, isn't it? I'm just left with the integral from 0 to 1, y dy. Okay, now I'll do this integral. This is just, so this will be k over 2, you know, it's y squared over 2, 0 to 1. It's just going to be a half again, isn't it? So it's k over 4. So this means, remember, all of this is equal to 1. All of this stuff is equal to 1. So this means that k equals 4. Okay, and so I can actually write the expression for our probability density function as 4xy times the indicator that both x and y are in the unit interval. Okay. Now, what I really want to know is the chance that the plane has gone down in that region there in the middle. Remember, looks like this. This is the region A, right there in the middle. What's the chance that it went down in there? Okay, so well then I guess that this is a third, and this is 2/3. This is 2/3, and this is a third. Right? So I'm just going to integrate that density function, but and with respect to both x and y, but just from a third to 2/3 and a third to 2/3. Okay. So I'm going to come in here and I'll say that the chance that the plane is in region A is, and of course this is all a guess, we don't know where the plane is, but assuming that this density function is correct, this is just going to be the integral from a third to 2/3, and then also a third to 2/3. Right? Dx dy. Now, these are the limits in the x direction, right? These are the limits in the y direction. They just happen to be the same thing for this case, okay? They just happen to be the same in this case. So this is going to be integral from a third to 2/3, integral from a third to 2/3 of 4xy dx dy, right? Now I'll do the integral with respect to x first, because it's the one on the inside, right? It's the one that is on the inside. So actually, I'm gonna pull that 4 all the way out. Pull the y out one time, because it's constant with respect to x. And I just have x dx and all of that times dy. Okay, so this will be 4 integral 1/3 to 2/3 y of x squared over 2 from a third to 2/3 dy. Right? This is going to be what's 2/3 squared is 4, so that's going to be 4/9 over 2. Oops, 49, 4/9. What's the difference? 4/9 over 2. It's 4/18. Yes. Minus 1/18, I guess. Third squared is a 9th, and divide by 2 is an 18th. Okay, so it's 3/18. 3/18 is 1/6. So this is 2/3. Then it'll be y squared over 2 from a third to 2/3. Right, the same kind of thing here again. I've got 2/3 squared is 4/9 over 2 is 4/18. Minus an 18th. That's 3/18. 2/18. Looks like it's a 9th. Okay. Now, notice that our answer here is 1/9, and the area of this region is 1/9. That is purely coincidence. That is a pure coincidence. Okay, maybe this is a really bad example. Actually, it's pretty good. I think now you should try to see if you can find the chance that the plane went down here in region B. See if you can do that. Region B. Here, I'll even set it up for you. Probability now that the plane went down in region B shouldn't this just be the integral? Let's see. X is going to go, or we'll do the y integral last, right? So let's see, double integral. I'm putting my y stuff on the outside. Y is going from 0 to 1/3, but x is going from 2/3 up to 1. See that? And then I need to put in my density function, which was 4xy dx dy. Okay. So see if you can carry that out. Okay. See if you can carry this out. Take a quick, easy little step there. Pull the line out. Got x dx dy. So do one integral and then do the other. Okay. See what you get.